So while we finish up this last module of the BC stuff, we're going to be looking at lessons 9.3 and 9.2. I'll take ideas from each and kind of put them together. So we won't be doing it necessarily sequentially in order. We're actually going to start with 9.3 and then we'll go back to 9.2 and then we'll finish up with 9.3 again. What we want to start with is finishing with the idea of an approximation. We started calculus this way with approximating slope, and we approximated slope by doing y2 minus y1, and we made our approximations more and more accurate. We then dealt with it in area, and we started with approximations of rectangles to help us with area, and then we did more and more rectangles to make it more and more approximate. The more rectangles, the better. So now we're going to be talking about how do we approximate functions and not only their slope but their concavity at the same time. So that's what we're building on. We'll start with what you already know. You already know about linearizations. A linearization is just another word for a tangent line. So that word is the same thing as finding a tangent line. If you recall that a tangent line, we needed to find a point and a slope. So here we have a point and we have the slope, which creates the red tangent line. We created this tangent line by finding the slope right here. The slope is the derivative. And here are the values of the point. The point would be point A and its corresponding f of a. This is the exact same as when we did tangent line of y minus y1 equals mx minus x1. It's the exact same rearranging. It's just taking that y1 term and moving it to the other side and having, so the slope would be the m value here, and then here is your ax value, and here's your function value. So it's the exact same. We're going to start using words like centered at. So we are centering it at this particular point, point A on our graph. So what the linearization, which we call L of x, and the original function, which we call f of x, they share a common point and they share a common slope. What they don't share is concavity. The blue f of x is concave up, while the line has no concavity at all. And we use that concavity argument to talk about overestimating and underestimating. In this situation, because the function's concave up, the linearization would be an underestimate of either direction, either an underestimate if we move to the right or an underestimate if we move to the left. So again, let's just practice working through a linearization to the function cosine of x. We're going to focus at the point x equals pi fourths. So looking at the graph, pi fourths is about right here. So we'll be focusing right there. And we want our linearization to have the common point and the common slope value. And we'll be creating a linearization right there that shares both. All right, so our point is going to be the value pi fourths, and then the cosine value, square root 2 over 2. The slope is going to be the value of f prime, which is negative sine of x. And so negative sine of pi fourths is negative rad 2 over 2. So the linearization and the function share the point and the slope. So my linearization is the slope, negative rad 2 over 2, times x minus the x value, which is x minus pi fourths, and then plus the y value. So that is my linearization. We'll use our linearization to estimate the value of cosine 0.75. So f of 0.75 would be the cosine of 0.75. and it would be really difficult for me to do that without a calculator. So instead I will approximate it, so we use the wavy circles, and we'll find L of 0.75 instead. So we're going to plug 0.75 into our linearization. So negative rad 2 over 2 times 0.75 minus pi fourths, and then plus rad 2 over 2. And that would be a very, very similar approximation to the actual value. They'll be very close to the real thing. Won't be exact though. And so the question is, will it over or underestimate the actual value? And so we focus on the concavity. So since cosine of x is concave down at x equals pi fourths, then the linearization of 0.75 is always going to be more than the actual value of 0.75 based on the concavity and the position of the linearization or the tangent line. What's new, what we want to introduce, is the idea of a quadratic approximation. So we're going to add in between the tangent line, the linearization, and the function itself, we're going to add something that has not only the common point and the common slope, but we're also going to add something that has the same concavity. And so we're going to squeeze that in. We're going to have a quadratic, a parabola, that's going to be right in between. It's going to be a better approximation. And what makes it better is that it follows the curve more closely, the original function more closely, than the linearization does. The way that we build that is we extend our linearization. So I want you to take a look. This is the part right here that is the L of x, that's the linearization part, and we're going to add to it or precede it with a power 2, okay, something that's squared. And so we'll take that same x minus a, and now we'll have a squared term, but that squared term is going to match the fact that it is a second degree derivative, and we're going to precede that with the fraction 1/2, which accounts for the chain rule, and so we're just going to take care of all that. We'll explain more about why it's 1/2 in a future lesson, but for now just know that it is 1/2. So that's how we're going to build a quadratic approximation. And again, this is better than linearization because it shares the point, slope, and the concavity. So now let's take a quadratic approximation. So we still need a point, we still need our slope, but now we're going to need our second derivative value as well. So we still have got the point pi fourths, and rad 2 over 2 for the cosine. We'll have the slope. The slope will be f prime of x, so the negative sign, or the negative sign of rad 2 over of pi fourths, which is negative rad 2 over 2. And then we're going to have the concavity, which will be f double prime of x, which will be negative cosine of x, or the negative cosine at pi fourths, which is also negative rad 2 over 2. So this is concave down. And so if we're looking at that position here, so at pi fourths, so we have our original tangent line in there. We are now going to be adding a quadratic, so a parabola, which squeezes between the cosine graph, so it shares the concavity of the cosine function. And so it's going to be more close of an approximation. So if we're going to build out the equation, so we will have what is q of x. This is the quadratic approximation, so it'll be 1/2 of the second derivative, so negative rad 2 over 2, times x minus pi fourths, and this is squared, and then minus the first derivative, which was also negative rad 2 over 2, times x minus pi fourths to the first, and then plus the y value. Now we can simplify that because you might notice that everything has a rad 2 over 2 in it. So another way we could write that would be to pull then maybe a negative rad 2 over 2 out. That would leave me with half of x minus pi fourths squared plus x minus pi fourths to the first, and then minus 1. That's another way to write that same quadratic. Now we want to consider how accurate this new quadratic approximation is compared to the actual value. Unfortunately, we can't use the concavity because they share the same concavity, so that's not going to give us any advantage. So we really just do a direct comparison of how close they actually are. Cosine of, so using my calculator, cosine of 0.75 is 0.731688, whereas my quadratic approximation of 0.75, when I use my calculator, is 0.731694. And so we're, down to the, 100,000ths of a decimal place. So the accuracy using a quadratic is incredibly close. All right, let's take a look at making a quadratic approximation at a different spot. So this time we're going to make our quadratic approximation at 0. And so we'll be looking for, all right, a tangent line there would, be pretty much perfect, would be perfectly horizontal. But if we create a quadratic, that will share the concavity there, and so will give us an increased value of accuracy. So we're looking at our point now is going to be the point 0, and then the cosine of 0, which is 1. Our slope will be f prime of x, which would be the negative sine of x, or the negative sine of 0, which is still 0. And then our concavity will be the second derivative, so that will be the negative cosine of 0, or negative 1. So we have negative concavity. So our quadratic approximation would be 1/2 times the concavity of negative 1 times x minus the x value of 0 squared. And then the second part of that would be the slope, so 0 times x minus 0, and then plus the initial point condition, which would be 1. So we'll simplify this to the negative 1/2 of x squared plus 1. So we get a really, really nice parabola that will help us estimate the value of cosine. So again, let's just estimate what this would turn out to be. So the cosine of negative 0.01 would be negative 1/2 times negative 0.01 squared plus 1, which comes out to be 0.99995. Without a calculator, we just leave it in its unsimplified expression. If we want to use our calculator to compare and see what the cosine of negative 0.01 would be, we get 0.99995, and then it would take us that many more before we actually got something different. So our quadratic approximation is a beautiful, beautiful model to help us estimate cosine. Our last one will be looking at a really challenging and complex. We've got a log combined with a trig. So we've got the natural log of the sine of x, and we want to compare it to the actual value. So if we are looking for our point, we'll be looking at pi fourths, and then the natural log of the sine of pi fourths. So that'd be pi fourths, and then the natural log of the square root 2 over 2. Our slope, okay, so that'll be the derivative, so 1 over the sine of x times a chain rule, which would be the cosine of x, which really is cotangent of x. And so we want to know what's the cotangent then of pi fourths. So that'll be 1. And then our concavity. So the concavity will be the derivative of the cotangent of x, which is negative cosecant squared of x. So then we're going to want what's negative cosecant squared of pi fourths. So that will be negative 2 over rad 2 quantity squared. In other words, negative 4 over 2 or negative 2. All right, so then we're ready to write our linearization and our quadratic approximation. So our linearization will start out with the slope of 1 times x minus pi fourths plus the natural log of the square root of 2 over 2. So that's our linearization. Our quadratic approximation will be 1/2 of the concavity times x minus pi fourths quantity squared plus, and then the same thing as the linearization. Oops, plus the square root, natural log of the square root of 2 over 2. And then we wanted to compare all of those things to the 3 different values. So our L of x, so L of 0.8 compared to Q of 0.8, sorry, I meant to write 8 there. And then we'll compare it to the actual F of 0.8. We should see increasing accuracy as we go along. So the linearization is negative 0.33197. The quadratic approximation, 0.332185. And then the actual function value, 0.332183. So just by making one tweak from a linearization to a quadratic, we've increased our accuracy significantly, which is pretty much the whole point. What we're going to be doing as we build this semester or this unit on is moving on to cubic approximations. We'll be moving on getting more and more accurate, and we're going to use calculus to continue to do that. All right, so we're nearing the end. This is the last of 4 lessons, and so we're almost there. All right, so keep up the good work. I'm really proud of all of you.